Now let's start getting into data mining through a tool that you already have seen earlier in the statistics course. We're going to look at all the different concepts that we discussed earlier on through linear regression. I'm going to first revisit regression from the angle that you learned it in statistics, so that then I can contrast it with how we take it for prediction, how we use regression in the data mining context of prediction. The first two videos are, again, just a recap of the traditional statistical approach to linear regression, where we use it as a descriptive tool to describe some kind of relationship in the population. Okay, I'll remind you again of the distinction between explanatory modeling, which is typically statistical modeling, versus predictive, and that's more of what we do in data mining. And the focus of explanatory is about either explaining or describing some kind of a population relationship. This is a slide that we had earlier on, and we described it in detail before. Another note is that recall that in explanatory or descriptive modeling, we're interested in the average behavior or in the overall behavior. We're not necessarily interested in predicting individual records. So first we'll look at the explanatory angle, and later on we'll look at linear regression as a predictive tool. Again, I'm assuming that you have taken a course in statistics and have seen linear regression being used. You might want to go back to your textbook from the core course to refresh your mind about what you learned there. But we will not be using it in the same way for prediction soon. If you're unsure of how statistics is used in the traditional statistical way, definitely watch these two videos and go back to the textbook that you used in your statistics course. In our textbook, we talk about regression from a predictive point of view. Okay, so here's what we're going to do. I'll remind you quickly how we run regressions, how do we interpret the output, how we check whether the model is valid or not, and finally, how do we test hypotheses. I'll use a small example that has only 128 records, but this is sufficient for illustrating the issue. So what we have here is a set of houses, and we have their prices and a bunch of properties of the houses, such as their square footage, the number of bedrooms, number of bathrooms, the number of offers that the house received while it was for sale on the market, whether the house was made out of brick or not, and finally, in which one of 3 neighborhoods in the city the house was located. Now, you can think of different types of questions. We can think of an explanatory question, such as, what's the pricing structure of houses in this city? And that's the question we'll look at first. Later, when we try and look at a predictive angle, we can set up a predictive objective, for instance, such as predicting the sale price of a house that just goes on the market. This could be of interest either to the sellers or to the real estate agency, or maybe even to potential buyers. So let's stick first to the explanatory objective of trying to describe the pricing structure of houses in Mid-City. Here's a little piece of the data. It's set up in an Excel sheet, and the file is available on the website. And for each home, and we have home IDs, we have the different measurements that I mentioned earlier on. Some are numerical and some are categorical. What's the process that we go through? We can think of this as a 5-step process, where the first step is we have to set up what's the input and output of interest. Obviously here, price is the output of interest. We're trying to explain variation in price. Then we have to think about which inputs are reasonable to use in a model for describing price. So number 1 is choose your X or input variables. Number 2 is start exploring the data and look at different charts of the X's versus the Y, maybe even of the X's versus each other. If you remember, when we have highly correlated predictors or input variables, that can cause some issues such as multicollinearity. After that, we can go ahead and fit a regression model with the input and output variables that we specified. And before we dare to use that model, we have to make sure that it adheres to the assumptions that linear regression model assumes. So we're going to go through this step 4 of checking the validity of the model assumptions, and that's typically done in a graphical way. Only after we're satisfied that the model is reasonably valid, only then can we use it to start answering the questions of interest, to start using statistical tests, confidence intervals, etc. So let's go through these 5 steps with this example. How do we choose the variables? Well, when we're building a descriptive or an explanatory model, we're going to have to use domain knowledge to determine which of the inputs really should be determining the output. And this is where you talk to a domain expert or domain experts and seek their advice in determining which variables to use. Assume that we're working with a real estate agent who's an expert in this city and has been selling houses in this city for a long time. This real estate agent would be able to tell us which of our variables, or maybe they even have additional data, are useful to include in the model. So they will tell us which variables to use. Now let's start looking at the data. And remember, we already have the data in an Excel spreadsheet. Later on, we'll look at using interactive tools. But for now, let's think about using even simple Excel, or if you're familiar with better tools, then go ahead and try them out. One type of chart that we have to look at is looking at the output of interest, which is price, versus each one of the predictors. That way we get an idea of which variables, input variables, actually seem to be correlated with the output. So these types of scatter plots are extremely important. As I mentioned earlier, we probably also want to see scatter plots of variables, input variables against themselves to see if there are ones that are highly correlated. Correlation tables are useful as well. When I have categorical input variables, such as neighborhood, what I might want to look at is, for instance, average price in each neighborhood, or the distribution of prices in each neighborhood. Side-by-side box plots would be really interesting and useful. I also want you to remember that scatter plots are limited. When I look at price versus square footage, that's not telling me the whole story about the entire relationship between all of the variables and price. So scatter plots are useful, but they are limited. So after we've determined which variables should go in, and we have an idea of what's going on in the data, and we've cleaned it in various ways that we'll talk about later on, such as thinking about extreme numbers, missing values, etc., I'm going to move to the next step, which is creating the variables or deriving the variables that are needed in order to run a linear regression. Now think again about brick and neighborhood. What kind of variables are these? These are categorical variables. In ordinary software, you cannot just plug them in and run a regression. Some software will allow you to do that. But really what you'd have to do before that is you'd have to create dummy variables. If I have 3 neighborhoods, we'd have to create 2 dummy variables that specify whether the house is in one of those 2 neighborhoods or not, meaning in the 3rd variable. For brick, since it's only yes or no, we need a single dummy variable. You'll notice that in the Excel file that is available on the website, we have not only the data, but also the different analyses that are mentioned in this video. I'll show you a very quick use of XLMiner, which is an add-on to Excel and has a very simple menu-driven approach. There is a multiple linear regression option, and when I choose that, the first window requests me to specify what are my inputs and what is the output. And again, here we're using price as the output variable, and the input variables are going to be all the variables that I had earlier on, but note that I replaced brick and neighborhood with the dummies. When I click Next, I can request additional information. And in this case, I'm going to request the extra fitted values, ANOVA table, and unstandardized residuals. And we'll see later on why we need these. And again, you probably remember from your statistics course that we want to see these. Note that in XLMiner, these are not the defaults. And the reason is that in prediction, these particular values are not necessarily what we're looking for. I run through these models, and again, it doesn't matter which software you use, and I end up with some kind of a regression model. Here we can see the output from running XLMiner with a specified linear regression. At the bottom, I see the ANOVA table, and I can see the F statistic that tests whether, as a model, these set of predictors are useful for explaining the variation in price, with their p-value, which is highly significant in this case. And in the regression model, at the top, the table shows me the coefficients for each one of the input variables, their standard errors, and their statistical significance. On the right, I have a few values. One of them is the multiple R squared, and another one is the standard error of estimate. And these two numbers are typical in any software that you would use. Before we do anything with this model, we have to check that the model assumptions are actually reasonably met. Because if they are not, and we come up with any type of interpretation of the coefficients from that model, we might be interpreting things incorrectly. So before we can use the model, we're going to go through this step of residual analysis where we're checking the model validity by graphically assessing whether model assumptions are reasonably met. To remind you what a residual is it's simply the difference between the actual output and the predicted output by the model. I'm using the notation EI, E sub I, to denote a residual for record number I. Y sub I is the actual output, and Y hat sub I is the predicted output using this model. Now, why do I have this little plate here? If you think of residual analysis as a more abstract operation, think about what a good chef does in a high-end restaurant. In order to make sure that the dishes that the restaurant is preparing are actually high quality and valued by the customers, one good practice is to actually look at the remainders that come back into the kitchen and see whether the residuals are showing maybe everyone is returning the lettuce. Maybe something is wrong with the lettuce. So looking at the residuals is a good detective way to inspect problems. Let's see what we're going to do. First of all, let's see which assumptions the linear regression relies on. I'll remind you that if we write the model as y as a function, a linear function in the x's, we have the betas that are the coefficients, and we have epsilon that is the noise. This epsilon, the noise, has several assumptions. One is we assume that the errors are normally distributed, meaning that, of course, we can predict a certain number, but the values can vary up and down. If we're predicting house prices for a particular type of house, then of course we can have different houses with the same specs that have different pricings. But the distribution of pricings is expected to be normal, to follow a normal distribution, a Bell distribution. We also expect that these errors have a mean of 0 and that the variation is constant no matter which x you plug in. So these are three assumptions: normality, 0 mean, and constant variance. The fourth assumption is that we assume that our records are independent, so that the price of one house doesn't actually affect the price of another house. Some of these assumptions are more detrimental in terms of affecting how interpretations will be correct or incorrect, and some are less detrimental. Still, we're going to go through checking each and every one of them. And we're going to do this graphically. Before we do this, just a quick calculation to remind you how to compute an error. So say we have a certain house, and the first house in our file has a pricing of $114,300. Assume that using the model that we just generated a minute ago, and you can try this yourself, assume that this generates a prediction of $103,182.88. The residual is going to be simply y1 minus y hat 1, and the direction matters. So the E1, the error here, is going to be $11,117.12. Of course, you don't need to do this manually, and in XLMiner, for instance, if you want to generate these residuals, just click the unstandardized residuals. How are we going to assess the different assumptions? We're going to look at a bunch of different charts of the residuals. So we generate the residuals, and then we're going to draw them in all kinds of different ways to assess the assumptions. First type of charts are looking at the residuals versus each one of our input variables. Residuals versus each x. If the x is numerical, we'll just draw a scatter plot. That's pretty easy. For instance, we can use square footage, which was one of our x variables. And you can see on the left-hand chart, we have residuals versus square footage. When we have categorical variables, we might look at something different, such as box plots. So a box plot of the residuals for each one of the levels, for each neighborhood, for instance. What we're expecting to see, if there is no assumption violation, is to see no pattern. So what we don't want to see is a pattern of any type. In this example, it looks like residuals versus square footage there doesn't seem to be any very obvious pattern going on. Remember that the sample here is quite small, so it's hard to determine whether there's really a pattern. For instance, when I'm looking at the residuals versus number of bathrooms, I might say, hey, for 4 bathrooms, there seems to be a smaller variance than for 3 and for 2. But that's not true, because we only have a single house with 4 bathrooms. So also keep remembering what's your sample size and what's going on besides just the shapes on the charts. There are some shapes that we know what to do with. So for instance, if we get a fan shape, and I'll show you an example soon, we know how to fix this. We don't just have to dump the whole regression. This is what's nice and flexible about regression. We can go back and instead of using that particular x, we'll take some kind of a transformation or a function of that x and rerun the regression. The second set of charts is looking at the residuals versus the fitted or predicted values, the y-hats. And in this chart, again, you see the residual values on the y-axis and the fitted values, the y-hats, on the x-axis. We don't want to see any pattern here. If we see a pattern here, then again, what we'll go back and do is instead of working, let's say, in price, we might use some other type of transformation or function of price. Maybe price squared, maybe logarithm of price, or something like that. The third assumption was normality. And in order to see whether the residuals are reasonably normal, we're simply going to plot some kind of a histogram or a box plot. A histogram is a nice simple plot of the residuals. And what we want to see here is a histogram that's reasonably symmetric around 0. This histogram is approximately around 0, but we see that it has a slightly heavier part in the positive numbers. This might again indicate that we might want to go back and work instead of price with price, we might want to use with some kind of a function of price, such as a logarithm or an inverse, etc. Last chart we'll look at is, remember the assumption of independence. We want to make sure that the houses are independent, that the pricing in one house doesn't affect the pricing in another house. And here what we do is we simply draw the residuals as a function of the house index. If we assume that the houses are ordered in our spreadsheet according to their sale date, then maybe that might be the factor that's influencing one house by the other. So we're just plotting a time plot, and notice that I'm using a line chart here to look at the residuals over time. And again, I don't want to see any pattern here. If I see a pattern, that might be indicating that house prices are affecting later house prices. Common patterns that are sometimes seen, especially when we have skewed variables, are fan-shaped, like the top right panel that you see up here. And this is indicating that the variation of the residuals is growing as the x value is increasing on the x-axis. When this is happening, this is violating the assumption of the constant variance. And in this case, again, we'll take this x that is plotted on the x-axis here and try and transform it. You can see other types of violations here where we see patterns, and I don't want to get into how we can correct them. There's plenty of literature on this online and in textbooks, and please go ahead and review those if you don't remember what to do. Now remember that these assumptions are critical when you're using linear regression for description or explanation. They're less critical when you're doing prediction. But it's always useful to just look at a few charts of the residuals. Sometimes a small transformation in the x or in the y might actually lead to better predictions as well. So what have we seen in this video? We started looking at using linear regression for description. This is again a recap of your statistics course where you learned about linear regression. We talked about choosing the x variables. We talked about plotting the data and looking at different scatter plots and perhaps other charts, and reminding you that those don't tell you the whole story of all the interdependence between the y and all the x's. Then we fit a linear regression using software, and we got an estimated model and an ANOVA table, and we could get residuals from there. And the last piece we talked about is validating that the model assumptions are reasonably met, and what to do if they are not met, which is go and transform your x's or y's and rerun the regression and recheck the validity of the assumptions. In the next video, we're going to get into the last step of using linear regression for description, and that is using this model that we generated and validated to test or infer this relationship in the population. So that's where we're going next.